Here's what we're going to do. We're going to live code. We're going to live code some code that involves threading and multiprocessing, and we're going to see if we take some code that has already been written, can we actually make it faster? Before I show you the starting point for all of this, I want to just show you one or two small conceits that we'll be using as we discuss. Behind the scenes, I have a very, very simple utility for timing code. It is not a very good utility for timing code. It just uses time.perfCounter. But you can see I can time the speed of running sleep for 1 second, and there's a little bit of noise here. It's not the best timer. But that's my general sense which I'll use in order to identify whether this code is fast or slow. Additionally, bear in mind that when we talk about these timings, we care about one particular time. If you ever use the time built-in your shell or the time program at the command line, you often see that there are multiple times reported when you time some process. There is the user time, there's the system time, there's the percent CPU, and there's the total time. This Python program that sleeps for 1 second takes 1 second of what we call wall clock time. That means that if we look at the clock on the wall, 1 second will elapse between when we start this and when we finish this. That is the time that we are concerned about primarily in this session. We're concerned about if we start a process at 5 p.m., is it going to finish by 5:30, or is it going to finish by 6, or is it going to finish the next morning? In addition to wall clock time, there's also CPU time, how much time the CPU actually spends churning through some computations. But we're going to assume that, you know what, we have a very beefy desktop. It's already burning through watts of power, kilowatts of power every hour of our time. Maybe we have a GPU in it that's almost about to melt. So we don't really care about CPU time. In fact, we want to maximize the amount of CPU time that we're using if that means that we can minimize the wall clock time. The distinction between the user space time and the system time is largely not particularly interesting for us. Whether the time is spent in kernel space or in user space, we don't really care. We just care if the thing starts at 5 p.m., when is it going to finish? Note that if we were to actually try to measure the utilization of our computational resources, we could look at things like the ratio of the wall clock time to the user space time or the CPU time. And here you can see if I put a busy wait that should wait for about 5 seconds, it doesn't use exactly 5 seconds of CPU time, but just running those Python bytecodes in that busy loop there is going to use at least 2 seconds of just churn through CPU time. But having said that, I want to share with you the other thing that is going to be necessary for us to work through this example. We have a REST API. It's not a particularly well-written REST API, but it is a REST API that we put together very quickly. In fact, we used Fast API to put it together. And it has a couple of endpoints. Part of what we want to think about is how do we take code that's interacting with the outside world that has both components that wait for something as well as components that do number crunching and make that code faster. And so here you can see I'm asking my REST API for its test endpoint, and I get some JSON output. I'm not going to worry too much about how this API is actually structured or the data that it passes back, although there are a couple of things that I do want to worry about. For example, this API is relatively slow. In fact, it has a hard-coded slowdown parameter that artificially slows it down. And if I run these endpoints enough time, I will eventually see these endpoints will fail. So this is an API that has some failure. I believe something like 10 to 25% of the time, these endpoints will fail, requiring that I query them again. And that's going to slow me down as well. Well, in addition to the test endpoint, I also have an endpoint that gives me information about what this API actually provides me with, which is information about some computational jobs that I've done. And so here you can see that jobs endpoint tells me the names of all the jobs, when those jobs were started, and whether they completed or not, whether they're still running or whether they have completed. And I can look at that information and get all of the names of these jobs. So you can see I have quite a few jobs that I've run, and I can see how many of these jobs are complete, and it turns out for all of these jobs, they were run a long time ago, they're all complete. For a given job identifier, I can ask that job identifier for its status. That is to say, not are you complete or not, but did you succeed or fail? In addition to the API succeeding or failing, the jobs themselves may succeed or fail, requiring me to add in some modality of, well, if the job failed, do I really want to get the API results for the job? There's no results, the job failed. But if it succeeded, I want to actually collect those results and do something with them. So you can see here this job failed, whereas this job hopefully should have succeeded. Given that, I can take a look at the results of the job. And the results of the job will be either job failed, there's no results, nothing actually got computed, or it errored out midway through, or something that I can easily put into a pandas data frame. Here you can see it's actually a fairly large result set. These result sets may be anywhere from 20,000 to 50,000 rows. Here you can see what appears to be the index column, some category. Well, I can use the requests third-party module. I can take these results, I can stick them to a pandas data frame, and I can see what this gives me. And it gives me some sort of category organized weighted value. So I might want to do things like weighted means on this data. Taking all of these pieces and putting them together, here is our starting point for our program. When somebody gave us this API, we said, okay, we'll write some code. It'll query for all the jobs. It'll take all the jobs and see which one's completed, because if it hasn't completed yet, we don't worry about it. From those jobs, we'll see which ones have succeeded. From the succeeded jobs, we'll capture all the data. Then we'll load that data into a data frame, and we'll do some analysis on the result. And so, simply as that, we're going to get all the jobs and grab the completed ones. Then we'll print that out to the screen, to our logging. For each job, we'll get the status, but knowing that that API endpoint could fail, we're going to do this in the loop until that succeeds. Once that succeeds, once the API call succeeds, we're going to ask if the job succeeded. Remember, the API can fail even if the job itself succeeded. So here, we're going to get whether the job succeeded, and if so, we'll note, okay, this is one of the succeeded jobs, and we'll print those out. And then for all of the jobs that we know have hit the success mode, we'll again query one more time until we get a successful API result. With the results, we'll grab those results, we'll put them into a list, we'll concatenate that list into a single pandas data frame, and we'll do a simple operation on this. We'll do a weighted value, a weighted mean here, a grouped weighted mean, which we know is a computational slow operation. And so there you can see that worked out well. Now, from a prototyping perspective, this actually worked out pretty well. You can see running with one job, it gave me a little bit over a second of an iteration loop, not the tightest iteration loop I've ever seen, but not so bad that I couldn't quickly set up all of the things I need to set up in order to interact with this API and write all the code to take those API endpoint results and give me something that I can do some computations on. The problem is, if I remove this break here and this break here, and instead of looking at just the very first succeeded job and the very first succeeded result for those jobs, I look at all of the succeeded jobs and all of the job results, this thing is kind of slow. I can take a lot of deep breaths in between each one of these steps. And what I might use is my simple timer to identify where that slowness is coming from. Because you can see I got 14 results, and I still haven't done my pandas analysis. There are many places in this program where there is slowness. And identifying that slowness and the nature of that slowness will help me better use tools like Asyncio, threading, and multiprocessing. And so, why don't we do the following? We will use our little built-in, a helper timed, and we'll just put a little time block around these. So we'll say with timed, and we'll say this endpoint here. Okay, very good. I'll comment out the logging output because that'll noise things up a bit. I just care about the times right now. I'll say with timed, and then here's our job status endpoint. And we'll see how long that took. And we'll comment out our logging, or actually, you know what? We shouldn't comment out our logging. If we are being good citizens, we'll use our basic config to fix that there. And then we'll put a timing around our job results endpoints. Here, we'll put one more of these around the pandas concatenation, which between you and me, I suspect is going to be kind of slow. And then we'll put one last timing around this final, here, this is the grouped weighted means, around this final computation that we do for our grouped weighted mean. So this is our group by apply. And Let's see what the times look like. So just that jobs endpoint took 1/10 of a second. That's pretty slow. And this is only like 25 jobs or so. This job status took 3.7 seconds, so maybe there's some speed that we can get back there. Ooh, the job results, that is very slow. 11 seconds. Just the pandas concatenation took more time than our API call here. And that group by apply, and let's actually not print this out so we don't scroll off the size of our screen. Here we'll just do a dot sample of this so we get a couple of the results. That itself took, I think, over 3 seconds, maybe as many as 5 to 10 seconds. Here what we can see in this program is there are many different sources of slowness. Now, there are many ways that we could address this slowness. We could remove the artificial sleeps in the API, but that's kind of beside the point. We could also identify places where we are doing some kind of number crunching and provide ourselves with more computational units for that number crunching. For example, we could upgrade our CPU. We could get a CPU with lots of cores and hope that Python automatically makes use of all those cores. Probably it won't. We could also make better use of the time that we're wasting waiting for these results to come back. Think about it. This job result endpoint is not doing any number crunching, at least not on our end. Maybe on the API end it has to do some things, but that's not really going to be captured in our timing, or I should say, that will be captured in our timing, but maybe some of this timing is just waiting for that entire data set to be serialized on one side and then unserialized on the other side, and just waiting for those API calls. We're just waiting for something to come back. We're not doing any computational work, and we're wasting some time. Another thing you can think is, from the structure of this code, we wait till we have all of the statuses, we wait till we have all the jobs, then we wait till we have all the statuses, then we wait till we have all the results, then we concat. Somewhere in the middle here, maybe we could interleave these a little bit. Maybe the moment we get a job status back saying, hey, this job is successful and there's results, we could immediately go and query the results rather than waiting for all of this to complete before we do this step. So there's a lot that we could do to interleave these operations, to move these things around, to see if we could capture some time of what appears to be just a little bit of math, about 20 seconds of work to compute 522,000 rows of results.